Electricity is the invisible force that powers almost every aspect of our modern lives, from the lights in our homes to the computers in our pockets. It shapes our economies, our technologies, our communication, our wars, and even our dreams. But what if this powerful natural phenomenon had been discovered not in the 18th century, as it was in our world, but more than 1,000 years earlier? What if, during the early days of the Islamic Golden Age, or perhaps at the height of the Roman Empire, brilliant minds had uncovered the secrets of electric power and begun to harness it for practical use? In this alternate history, we imagine a world where the discovery of electricity happened around the year 700 CE, a time when much of Europe was still in the Dark Ages, but the Islamic world was flourishing with scholars, engineers and philosophers who had access to ancient Greek, Indian and Persian knowledge. In our new timeline, a Persian scholar working in the libraries of Baghdad, inspired by the writings of ancient thinkers like Thales of Miletus and Indian treatises on natural forces, experiments with amber, silk and copper. He observes that when rubbed, amber attracts light objects and produces sparks. He theorizes that this is a kind of natural force, unseen and mysterious, yet very real. By crafting crude electrostatic machines, simple devices with spinning wheels, silk and bronze, he is able to produce larger sparks. He calls it the fire of the air. Within a decade, other scholars take up the work, including Al-Kindi and the mechanical genius Al-Jazari. The House of Wisdom in Baghdad becomes the epicenter of an early electrical revolution. Soon, these inventors develop something like a battery, inspired by ancient Mesopotamian jars lined with copper and zinc, filled with vinegar. They use these devices to create small, controllable currents. At first, they are used for novelty, lighting up thin filaments or sending tiny shocks through wires to surprise guests at court. But quickly, applications grow. Lamps are designed that glow faintly without oil. Electroplating is used to create beautifully coated metals and ornaments. Simple electric bells begin to ring in mosques and temples, triggered by motion or time. Water wheels now incorporate primitive electric pulleys to raise water more efficiently. By the early 800s, Baghdad's palaces and libraries feature electric lighting systems powered by rechargeable clay pot batteries, and scholars debate the potential of electric forces the same way later scientists would debate gravity and magnetism. Meanwhile, word of these wonders spreads along trade routes. Travelers from Byzantium, India, and even China come to witness Baghdad's marvels. The Byzantine Empire, still strong in Constantinople, adopts the knowledge. Electric lamps appear in churches. Hospitals begin using mild electric currents to treat muscle pain. Architects design towers lined with copper to capture lightning, protecting large structures. These lightning towers become both scientific tools and religious symbols. The Byzantines call them the pillars of Zeus's fire. As centuries pass, science advances steadily. With electricity at their fingertips, medieval engineers begin to rethink how machines work. Watermills and windmills now use electrical relays to operate multiple tools at once. Artisans develop electroheating devices to control the temperature of furnaces for metal and glass. Engineers experiment with rotating magnets, discovering the basics of electric motors. Hospitals develop static shock treatments for a range of conditions, and theories about the nervous system develop far earlier. Education expands. With electric lamps allowing nighttime study, universities in Baghdad, Constantinople, Cordoba, and Cairo blossom into international centers of innovation. These schools not only preserve ancient knowledge, but build upon it. By 1000 CE, the use of electricity becomes widespread in the Islamic world, Byzantium, parts of India, and northern Africa. A massive electric observatory is built outside Cairo, using motorized instruments and sensors to track stars more precisely than ever before. Sailors begin using electric compasses based on magnetism to navigate, allowing trade ships to reach India and China faster. Europe, still emerging from centuries of fragmentation, begins to catch up. When the Crusaders arrive in the Middle East, they are stunned to see electric street lamps, doors that open with the wave of a hand, and fountains controlled by electric switches. They return to Europe not only with spices and silk, but with manuscripts and machines. Slowly, electricity begins to seep into the courts of France, Germany, and England. But not everyone embraces the new power. In some corners of the world, religious leaders see electricity as a dangerous force, perhaps divine, perhaps heretical. Debates emerge over its use in temples, and whether human beings should control such energy. Still, its usefulness in war cannot be denied. By the 1100s, armies are using electric signals to communicate across battlefields. Special electric traps and wire fences defend cities at night. Elite soldiers use armor that includes electric padding to resist impacts and increase strength slightly using assisted motion joints. Siege machines use drills powered by motors. The Mongol hordes under Genghis Khan encounter electrified city walls in China and Persia, slowing their conquests. In India, massive temples use electric mechanisms to move giant stone doors, preserve food, and power irrigation pumps. Agriculture booms, and urbanization increases rapidly. By 1200, global empires are shaped not only by their armies, but by their engineers. The Mali Empire in Africa, trading gold and salt across the Sahara, begins building electric workshops in Timbuktu. Chinese dynasties, already using gunpowder, now develop basic electric cannons that fire metal projectiles using magnetism. These are crude railguns, dangerous and unstable, but they signal the merging of chemistry and electricity. Technology spreads faster. A new generation of scholars writing in Arabic, Persian, Greek, Sanskrit, and Chinese builds the foundation for an industrial revolution far earlier than in our real timeline. By 1300, large cities across Eurasia are connected by electric telegraph lines, allowing messages to travel in minutes rather than weeks. In Egypt, the first electric train is built to move stone along the Nile. In the Mongol successor states, factories powered by motors begin to appear. In Europe, newly translated works of electrical theory begin to spark local innovation. The Renaissance comes not just with art and humanism, but with volts and magnets. Leonardo da Vinci writes about electric circuits and designs advanced electric wingsuits. Scientists in Florence and Paris argue about alternating and direct current. Universities across Europe build labs to replicate Baghdad's early devices. Colonialism unfolds differently, with electricity-based machines reducing the need for slave labor and increased global communication. The Atlantic slave trade is far smaller. African empires with access to early electric technology modernize faster, and many resist European colonization effectively. In the Americas, native civilizations receive electric tech before conquest. The Inca build high-altitude power stations using water flow. Mayan cities use electric lamps in temples. When European explorers arrive, they face opponents who are technologically advanced, forcing trade rather than domination. The 1500s bring a second wave of innovation. Electric navigation tools help explorers reach the Pacific Islands and Antarctica. Early electricity-based air balloons allow humans to reach the sky centuries before the Wright brothers. Science fiction begins to emerge as a genre with tales of electric cities on the moon and machines that can think. The printing press spreads faster thanks to electric typesetting machines. Literacy rates soar. By the 1600s, machines can perform simple logic using electric switches, the birth of computing. Pascal and Leibniz designed protocomputers. The foundations of programming are laid centuries ahead of our world. By the 1700s, global civilization looks radically different. Asia, Africa, Europe, and the Middle East are in technological parity. No single continent dominates. Peace treaties and alliances are mediated through global electric communication networks. Wars still happen, but diplomacy and trade are faster. The Industrial Revolution occurs around 1720, powered by both steam and electricity. Trains, factories, and electrical plants rise across continents. Education becomes universal in many empires. Hospitals use electric sterilization. Electric microscopes are built to study diseases, and the concept of germs spreads quickly. In the 1800s, electric aviation takes off. Short-distance flights powered by magnetic propellers begin between major cities. Radio waves are discovered and used for communication. Space science begins to mature. Telescopes and orbit prediction tools allow scientists to consider missions beyond Earth. By the late 1800s, a coalition of world scientists develops a plan to launch a satellite using an electric rail launcher from a mountain peak in Tibet. The launch fails, but the age of space dreams begins. In 1850, a world war erupted, fought with electric tech, fast planes, and wireless signals. It ended quickly, leading to a global peace alliance. By 1930, humans landed on the moon. Mars colonies rose by the 60s. AI matured by 2000. By 2025, the world was 1,000 years ahead, yet the human heart stayed the same. Technology moved us forward, but wisdom shaped our path.